Hello, welcome to today's lecture on deep learning, where we'll discuss the transformer architecture. So on the last lectures on the attention mechanism, we have introduced the attention mechanism as a way to perform queries on key value pairs using neural networks. We have introduced self-attention as an important architectural component of neural networks that uses the attention mechanism, where each representation at, for example, a token in a sequence would attend to all the other tokens in the sequence to compute a weighted average of all the tokens in the next layer. And today we will introduce the so-called transformer architecture that leverages self-attention to build large neural network architectures that are state-of-the-art today for the analysis of sequences, but also images. So the advantage of the attention mechanism is that self-attention allows a lot of parallel computing. So if you have a lot of parallel computing, that means that you can build very large neural network architectures and just increase the number of processors to perform more computations in parallel in order to train them. It also has the shortest path length. So each element, for example, or in a sequence, in just one step of self-attention can attend to all the other elements of the sequence. Now, while early neural network architectures that applied self-attentions to sequences have combined them with recurrent neural networks, a group from Google has actually shown that a architecture that only depends on repeated blocks of self-attention is sufficient to model sequences end to end. And this is the so-called transformer architecture, without the need of any recurrent or convolutional layer. While this paper was originally proposed for sequence-to-sequence learning, today they have also been used for images. They're basically pervasive in all kinds of applications of modern deep learning. Applications to language, vision, speech, and reinforcement learning. Here we see the transformer model, the architecture that has been proposed in a paper that is called Attention is All You Need. So it's a sequence-to-sequence architecture. So we have sources and targets. The sources are put into an encoder, and then the target sequence is created by a decoder. So the transformer is composed of an encoder and a decoder. The sources are tokens of a sequence. Thus, we want to add positional encodings to keep track of the position in the sequence. So the embeddings of the sequence tokens are enriched with positional encodings. So we add positional encodings to our matrix X. And then we see that both the encoder as well as the decoder stack multiple of these modules that are all based on self-attention. So here we have a multi-head self-attention, and here we have a multi-head self-attention. And we basically have groups of these layers that are stacked in modules that are then repeated multiple times. Let's first look at the encoder, which is a stack of multiple identical layers. So each of those blocks consists of 2 sublayers. The first sublayer is a multi-head self-attention pooling. So it takes the embeddings of the input tokens with their positional encodings and performs self-attention to those multiple times, so multiple heads. It also copies over the inputs to the output of this multi-head self-attention. So there is a residual layer. So this here is residual layer. So if Y is the output of the multi-head self-attention and X is our input to the multi-head self-attention, we would here copy X over and thus in this point compute X plus Y, such that the information about X is still contained here after the self-attention, because we're computing the sum of X and Y. So this is the first part. The first sublayer is this multi-head self-attention with this residual layer here. The second one is then a position-wise feed-forward network. So position-wise means that it will treat each token independently and compute a feed-forward network to transform the D dimensions of this token into the output dimensions using a multi-layer perceptron. And it will use exactly the same multi-layer perceptron on each token, so using the same weight matrices and biases. And then the output of that is again added to the input using another residual layer. So they're called residual layer because they're inspired by the ResNet architecture that introduced residual layers in the context of convolutional neural networks applied to images. So these 2 blocks are then repeated n times to build the encoder. So the encoder has an output, and this output of the encoder is then passed over to the decoder here in this multi-head attention module. So let's look at the decoder now. So the decoder also is a stack of multiple identical layers that again have residual layers between all of those layers and normalizations. It starts out with a self-attention based on the positional encodings, but it's a masked self-attention. We will get to that in a moment. Let's start out with this attention module here that takes as key value pairs the outputs of the encoder and uses queries here that come from the targets. Then again, using a residual component, the output of the target token embedding is added in a residual way after this attention. And then again, we have a position-wise feed-forward network. And then also this part is repeated then n times. Now, why do we have here a masked multi-headed self-attention for the input embeddings. So the input embeddings are basically you're saying, okay, I want to evaluate my sequence at the following positions. So you take the input features of the tokens, you add the positional encodings of those, and you perform self-attention. It's masked because when you generate a sequence for each of those target tokens, you want to attend only to the tokens that you have already generated. So you're using masking to ignore all the tokens that have not yet generated, such that you only attend to past tokens. In this way, the decoder retains its autoregressive property. Autoregressive means that you are generating the next token based on the past tokens. The output of this masked self-attention is then used as the queries for the multi-head attention that uses keys and values based on the output of the encoder network, and then passes that to the position-wide feed-forward network and performs this whole thing multiple times. So each of those blocks is repeated. Remember, position-wise feed-forward networks transform their representation. So we see them here, we see them here. Of all the sequence tokens using the same multi-layer perceptron. So they use the same feed-forward neural network and apply it to all the tokens in a sequence. They basically transform an input tensor that has the size, batch size times number of sequence time steps and all of those feature dimensions into an output tensor of the same batch size and the same number of time steps, but might have a different number of output dimensions. In this case, actually, the input and the output dimensions have to be identical because we're always adding these residual connections. In order to be able to add the input to the output, they, of course, need to match in dimensions. Now, this was already all about the transformer architecture. So you just take these self-attention mechanisms and you stack them on top of each other many times to create an encoder of your sequence. Then you use self-attention to transform the locations of the tokens where you want to generate new samples of your sequence, also using self-attention to generate a set of queries. These queries then query the embeddings generated by the encoder in order to create the outputs of the decoder. So the transformer is an instance of the encoder-decoder architecture, and you could, of course, use both the encoder or the decoder individually. In the transformer, multi-head self-attention is used for representing the input sequence and the output sequence, though the decoder has to preserve its autoregressive property because we want to attend only to already generated token when generating the next token. So thus it employs this masked self-attention layer in the decoder. All the attention layers and the position-wise feed-forward network layers add residual connections where you not only compute the output but also add the input of the corresponding layer back into the output, and layer normalization. And as we will see, that residual connections and layer normalizations help in building extremely deep neural network architectures. Remember, these blocks are repeated multiple times, so there can be many of these layers. The position-wise feed-forward network is in the transformer model transform the representation at all the sequence positions using the same multilayer perceptron, so a feed-forward neural network that use the same weights to all the tokens in the input sequence and the generated sequence. And with this, I want to say goodbye and see you next time.